What is going on, everybody, and welcome to a Reinforcement Learning with Stable Baselines 3 tutorial series. So Stable Baselines 3 is to reinforcement learning like sklearn is to general machine learning. The idea here is to abstract away some of the more complex and nuances of writing and applying these reinforcement learning algorithms and sort of homologize the entire experience such that once you've created your environment and you can essentially just try all of these various algorithms really quickly, really easily, and just kind of get a lot of the code written for you that you're going to have to write every single time. And so, at least for me, when I was embarking on a recent series for the simulating robots and doing reinforcement learning to try to teach the robot how to walk, I did indeed find this very challenging to apply these existing reinforcement learning algorithms to some environment. And then if you want to change it or anything like that, it becomes just a massive headache. So anyways, eventually stumbled into Stable Baselines and found it to be unbelievably easy to use, so I highly recommend it. So with that, to use Stable Baselines 3, you're going to need PyTorch. That is the backend that they use. So you can come here and install PyTorch. This is pytorch.org, and you can get started. And then also you will need Stable Baselines 3, which is just a pip install stable-baselines 3, and then the extra stuff. I don't actually know if you will need the extra. I don't know what's included, but grab it anyways. So once you have that, let's go ahead and get started. So we will be using OpenAI Gym as well. I believe Gym is included when you install it, but I don't actually see anything specific here. But you also might need to do a pip install Gym, and then also possibly some of the extras. But I think we're just going to be using the 2D environment, so a pip install Gym might be successful. But if not, check the description. So I'll throw something in there. There's also a text-based write-up, so if we have any problems, I think it'll be fine. I think the only thing you'll need here, I'll copy and paste this in here. You'll need the box 2D. So pip3 install gym box 2D. That's all we're going to use from the gym. And obviously, eventually, we'll use a custom environment. I'll show you guys exactly how to do that as well. But for now, to keep things simple, we're going to use the OpenAI Gym environments. So before we get too deep into that, I could spend a whole bunch of time on all the theoreticals of reinforcement learning. I'm not going to do that. I think the best way to learn reinforcement learning is to jump in, and if you find an algorithm that works really well, then you can dive in and learn more about that algorithm, but I think you're going to learn by using much better. So I won't get too deep into the weeds, but what I will say is we are going to cover some terms that you must know before you get into this. So first of all, we have the environment. This should be fairly obvious, but it's what you're trying to solve. So cartpole, lunar lander, some other custom environment. If you're trying to make some AI play a video game, the game is the environment. Then you're going to have model. So this is just basically what algorithm are you using. It's your specific trained algorithm is your model. Then you have agent. This is the thing that's interacting with the environment, so and using that algorithm or model to do so. Then you'll have observations or states. What's the state of the environment? This could be like imagery or visuals, or it could be other vector information like sensors and stuff like that. You have an action. These are basically what is your agent going to do in that environment, essentially per step. And that's another term, is just simply the step. So when you step an environment, you quite literally just take a step. In general, you pass your action to some step method. The environment performs that step and returns a new observation and reward for you to continue in this kind of loop until you're done. So if you think in terms of like frames per second, if you're playing a game at 30 frames per second, then you have 30 steps that you would take per second. It can get far more complicated than this. A step is just simply progressing in the environment. And then finally, when it comes to action spaces, you have discrete or continuous actions. You can think of discrete like classifications. Cartpole, for example, has a discrete action space. You go left or you go right. It's nothing in between. There's no like continuous values here. It's left or right, not somewhat left, somewhat right, and so on. Discrete. Then you have continuous. You can think of continuous like regression. It's a range of nearly infinite possibilities. The bipedal walker environment is a continuous action space, as is much of robotics, because you're going to set the servo torque anywhere in a range between, let's say, in the example of bipedal walker, -1 and +1, or a servo position. It's not always going to be torque. Typically, a continuous environment is harder to learn, but sometimes this is a requirement. So again, in robotics, this tends to be more of a continuous type problem, even though servos are actually discrete with something like 32,000 positions. That's far too many discrete positions to pass into your neural network. So instead, we treat this as a continuous problem. But those can be converted into, often a continuous problem anyways, can be converted in various ways to a discrete problem. And more on that later, and why we want to do that. More on that later too. So assuming you all have Gym and Stable Baselines 3 installed and PyTorch, obviously, let's go ahead and run through some of the basics of Gym and these environments and how things are working. So we'll import Gym, and then env will be gym.make. And in this case, we're going to make Lunar Lander v2. As an aside, I've been coding almost entirely with Copilot, and it's so painful writing things out completely. I've been super spoiled. So every time you have an environment, before you can actually step in that environment, you have to do an env.reset. So we'll go ahead and call that. And then we can print sample action. And we will do env.action space dot sample. So we're just going to see an example of what is an example action for this environment. And then we can also print observation space shape. And we will say env.observation space dot shape. So painful typing things out. Print, and we'll do a sample observation. So sample observation, and we'll make this env.observation space dot sample. Yeah. So, and that's a method. Cool. All right. So once we have those things, let's go ahead and finally close this off with an env.close. And let's go ahead and run that. Get rid of this. Cool. So sample action, you can see here is a 0. If we run it again, possibly we'll get something else. Right. So just an example there. So your observation space shape is just a flat 8 values. And as you can see, these are the 8 values. Honestly, I don't even know what they are, but it's just as you get into reinforcement learning, this is what I mean by, I think, the harder part of reinforcement learning is less about the algorithm. Yes, you can tweak some of the hyperparameters in your algorithm, but in general, it's going to come down to your environment, your reward mechanism, and your observations. So like what you feed in to those algorithms, especially by now, are pretty robust algorithms. I mean, they still take a very long time to train in that regard, but if it's going to learn, it will learn, and changing those hyperparameters won't do too much. At least you can screw it up, but from the baseline values, the default values, I have found, I can eke out maybe an extra 5-10% performance possibly by tweaking hyperparameters, but for the most part, the actual gains that you're going to make are going to come from algorithm choice, but also like reward mechanism and your observation space. So anyways, keep that in mind. So these are just some examples of kind of what we're working with. So in this case, our observation is just, this flat vector, and then we have an action space of certain values that we can pass. So, and this is hopefully the fact that, we don't even need to really know what these values are should kind of show you how robust, I suppose, Stable Baselines 3 really is, because you'll see as we go to train a model on this environment, it's not that Stable Baselines 3 just knows the lunar lander environment. That's what's so nice about Stable Baselines 3 is if you decide later you want to change something about your observation or your reward mechanism or anything like that, you just make the change in your environment. You don't have to touch your algorithm at all. And that's what makes it really, really helps. It saves so much time. So let's go ahead and see an example of our environment in action. So if we go ahead and do 4-step in range 200, we'll do env.render, and then we will env.step, and in this case we're just going to pass a random action. So env.action space dot sample. So we'll just do a random action here. So we'll go ahead and run that. And here we have our agent. So it just ran for 200 steps. That was actually a really good, really good example. Let's do another one. It's not the worst random. Usually it's like flies around. Not bad. Okay, so yeah, so we have that. Also, that's like really small. Let me. Okay, that looks better. So hopefully we'll be able to actually see what's going on. So I'll kill that. Hopefully that'll go away. Cool. Okay, so that's just a random lunar lander. Now, one thing we can do is every time you take a step, you actually are getting back an observation, a reward, whether or not the environment is done, and any extra information that you might care about. So let's go ahead and print reward, and then I'll change this back. I made it 5200 just so I could modify the recording. So we'll run that, and then we can kind of see here. So these are just our rewards, essentially. And since it eventually crashed, we got a negative 100. But here you can see the rewards are whatever they are. And again, it's almost irrelevant as long as we can assume the environment's been made reasonably well, which we know the OpenAI environments have. When you go to create your own environment, it's completely a different story, but we'll get there. So now what we want to do is train an algorithm on this this environment. So what are some of the things that we know about Lunar Lander? Well, the only thing we really need to know which algorithms we can work with is it discrete or continuous? And in some respects, that can actually get even more complicated, especially with like there's discrete and then there's multi-discrete. So what does that mean? So if you have discrete, that would mean what we have here, which is just discrete. Your actions is you have one action choice per step to make, whereas you could have multi-discrete. Like, so in the case of like a robot, for example, you're actually trying to get servo positions for, let's say in my example with doing the Biddle robot dog, there's 8 individual servos, all that need predictions to be made. So that's a multi-discrete problem, for example, if you're using a discrete algorithm anyways. So to know what we can use, we can come back. So to know what we can use, we can go to essentially the homepage here, go to RL algorithms, and they have a lovely little table. It almost reminds me of scikit-learn initially, which algorithm to use. It was like this like walkway path thing. I have many memories of like revisiting that over and over for various projects. But anyways, we can see here, what things can we work with? So in this case, so box, you can think of box as this is your continuous. Discrete is like the classifications, and then multi-discrete, whether or not that's supported, and then multi-binary. Essentially, that's going to be the same as multi-discrete. It's just binary. So now what we're going to do is we can check out, let's just do the first one on the list, because we're just going to say, okay, we want to do discrete. Cool. Which of these algorithms can support discrete? And we can see there's a huge list that we can choose from. So we'll just start with A2C to start. So how do we do this? So again, imagine that this is like, it doesn't have to be the Lunar Lander environment. This could be your own custom environment, which again, we will get to soon. So you have this environment, and what you want to do is test one of these algorithms on your environment. So to do that, it's just so simple. From stable baselines 3, we're going to import, and we will first bring in A2C, all caps. So from here, what we want to decide is essentially, once you have your environment, we'll go ahead and I'll reset there, and then we'll come down here, and then all we want to do is first define our model. So we'll say our model is equal to, in this case, it's A2C. This is a MLP policy, so MLP police policy, and we pass env. And then verbose we'll set to 1 for, and we'll cover like TensorBoard later and stuff. But for now, this is pretty much, I think I've changed a lot of algorithms, and I'm pretty sure I haven't touched this. Obviously, multi-layer perceptron. I don't even know what the other policies are, but obviously there are other ones. I think that's just so it doesn't have to be fully connected. I don't know. Maybe that in a distant video. But so far, through my personal uses of stable baselines 3, I don't think I've ever changed this line at all. I think I'm just editing what algorithm we're using. Anyways, now to train. Model.learn. Boom, done. So here we specify how many total time steps. How did you know that that's what I wanted already? Interesting. Have to double check Copilot. Total time steps, 10,000 we'll set for now. So this will train for 10,000 time steps. It should go very, very quick. And then we will instead do, I kind of want to change this code for 200 steps, or do we want to just let it go? I'll just let it go. We'll say, well, the correct way you would normally do this, I'll just write it out. Episodes we'll set to 10, and then we're going to say, so for ep in range episodes, what do we want to do? Well, rather than for step in range, we're just going to say, first we'll start with obs equals env.reset. So other than step, this is the reset method also returns an observation, but nothing else. There's no reward because you just reset the algorithm. There's no info to pass or anything like that. So it just will return an observation. So we will grab that observation. We're going to set done to be false. And then we will just simply, while not done, we will do this. I'm no longer going to print the reward. I don't want to see it. Also, stable baselines 3 will give us a little output of information, so no need. So I'll go ahead and save that, and I think we can display it in here. I think that'll be fine. So let me make sure I did everything somewhat decently. I guess we'll find out. Go ahead and run it. So first, we'll start training. We're already 1,000 in. 1,000. Let's make this a little bigger so we can actually see it. So this is the length of the episode. So how long is the agent surviving? Sometimes that's a very useful metric to know. And then episode reward mean. This is just telling us what is our typical average reward per episode at this time step. There's other information here like frames per second, iteration, all this other stuff. Sometimes this will be important to you, sometimes not. So after 10,000 steps, we can see this is our agent. And actually, given what I showed you before of the random agent, this doesn't look too far off of the random agent, but I assure you the random agent is worse than what we initially saw. But as you can see, it's not very good. So the next thing that we could do is increase the time steps. So we can go for 100,000 steps instead of just 10,000 steps. And if you're wondering about saving and loading and all that, that is the subject of the very next video. But for now, let's train this for 100,000 steps. Okay, moment of truth. Here we go. Honestly, that's not looking... Oh. Not very good. At least the episode reward, average episode reward did come down. But that's still not that great. That's not the best that I've ever seen, right? So yeah, going up. Wow, it actually, interestingly, so in this case, episode reward mean, and then we come down here. It looks like it got even worse over time. So I don't have the full history here, unfortunately. We will get to TensorBoard logging soon, the next tutorial. But for now, as you can see, it was decent at around 70-ish thousand steps, and then eventually just kind of went bad. So this is why in the very next tutorial is going to be saving and loading models and saving as you train models, because this sort of thing is not uncommon. But just to show you, now you've got A2C, which is a, not as robust algorithm. We also have PPO. So literally, to try an entirely different reinforcement learning algorithm, you just import it, and then we change it right here. And that's it. Now we use PPO. So again, we'll do the exact same thing. I'll just go ahead and run this. And we'll run this again for 100,000 steps, and we'll see what kind of difference did we get. So we ended here at negative 48, but at some point we did actually get a reward of like 50. So anyway, I'll be back when this is done. Okay, so we have our result, and in this case, again, it's very hard to compare these two algorithms because they both look quite bad after only 100,000 steps. I mean, it's better than random, but it is comical how my random example worked pretty well, and then the trained examples didn't. In reality, we are training these models for far too few steps, so we need to train them longer. But as you can see, even like when we did the first 10,000 steps, well, when we decided, okay, let's try 100,000 steps, well, we had to retrain the model all over again. So what really we want to do is be able to save, load, and then track performance and all that. So that's what we're going to be doing in the next tutorial. In this case, the only standout difference, one is it trained maybe 10% faster than the A2C model did. And then also it's staying alive a lot longer on average. But again, like I said, neither of these models even remotely close to their actual training time. So to put that in perspective, generally you're going to do millions of steps. So, 10 to like 100 million steps. I can imagine there are some environments where you might even do more than that. But anyways, yeah, so by this point, hopefully you have a pretty general understanding of Stable Baselines 3, reinforcement learning, kind of what are the main, terminology like observation and actions and steps and all that kind of stuff. And in the coming tutorials, we'll hopefully show you how to actually start using this to train a model and kind of track its progress over time. And then eventually how to apply this to truly a custom environment, a custom problem, and really get into the nuts and bolts of what I think makes reinforcement learning hard, which is actually engineering your own environment entirely. It has really nothing to do with these algorithms. If you're interested in learning more about neural networks and how they work, then you might want to check out Neural Networks from Scratch, a book by myself and Daniel Kukiewa, inside of which you'll learn how to code neurons, activation functions, how to calculate loss, do optimization and backpropagation, and of course apply everything that you've just learned to a problem. The book itself is in full color for graphs and code syntax highlighting. Everything's on high quality pages with full font and a comfortable line spacing to make reading easy. Finally, every concept, including the math and coding, is broken down into the truly atomic parts and then put back together step by step to give a full understanding of neural networks and how they work, including all of the math behind them. By the end of the book, you will have created your own neural network framework from scratch. This is the book that I wish existed when I was learning deep learning, and I'm extremely happy to be able to offer it to you. If this sounds interesting to you, then you can head over to nnfs.io to learn more and buy yourself a copy. So anyways, that's all for now. Thanks for watching, and I will see you guys in another video.